Hello and welcome to another slide video from the Cornish Radio Amateur Club in preparation for the RSGB Advanced course, which ultimately leads to the issuance of a full license. And today we're going to look at antennas and aerial tuning units, also called aerial matching units. So let's have a quick look at the syllabus. 5C1 says, recall the equation for calculating half wavelengths and be able to apply n-factor correction in calculating the approximate physical length of dipole elements. Well, of course, you can already calculate the what half a wavelength is, given the frequency, and this is a slight correction to actually make the physical length of the dipole. Remember that V equals F lambda or lambda equals V over F, and its other form is the one you use for calculating wavelength, and you simply divide it by 2 to get the half wavelength. So 5C1 talks about the corrections necessary for velocity factor and end capacitance, so we'll be going through that in a minute. 5C2, recall that the angle at which the propagated radio wave leaves the antenna is known as the vertical angle of radiation, and that the longer distances require a lower angle of radiation. We don't cover this too much in this presentation. It's sort of self-evident. If you beam directly upwards, no matter what frequencies you're on, it's not going to be terribly useful unless you wish to communicate with satellites. On the VHF and UHF frequencies, if you beam upwards, well, apart from satellites, nobody's up there. And on the HF bands, a low angle of incidence to the ionosphere will give you a greater communication distance. So we don't really cover that very much, but we do cover it a bit better in propagation. Recall the effect of the ground on the angle of radiation. We will be covering that as we go through. Recall the current and voltage distribution of the dipole and quarter wave ground plane antennas. Recall the feed point impedances of half wave dipoles, quarter wave and loaded 5/8 antennas. Now we'll be going through that in some detail, looking at the voltage and current distribution and hence the impedances over the lengths of the antenna. And for that we need to loaded 5/8 verticals, folded dipoles, full wave loops and end-fed quarter and half wave antennas. Recall the effect of passive antenna elements on feed point impedance and the use of folded dipoles in yagi antennas. Right, 5C4, identify folded and trapped dipoles and quad antennas in addition to those in earlier syllabuses. Now, I haven't covered all the antennas that were covered in the foundation and the intermediate licenses. It might be worth you just flicking back through the syllabuses there and having a quick look and just recalling what they look like. In general, I think it's pretty much covered again in the advanced course, so I don't think there's too much to worry about there. 5C5, recall that an antenna trap is a parallel tune circuit and understand how it enables a single antenna to be resonant and have an acceptable feed point impedance on more than one frequency. So we'll be looking at trap antennas and going through those in some detail. Recall that this technique may be extended to multi-element yagis, antennas rather, such as yagis. So the traps can also be put into reflectors and directors, and we'll be covering that as well. Okay, so what is an antenna? Now we don't need this for the exam. Again, this is a bit of background. We can say that it's any conductor with an AC signal will to some extent radiate electromagnetic waves at the frequency of the signal. Of course, if the conductor is of trivial length, that hardly applies, but as the conductor gets longer and longer and longer, it will to some extent radiate electromagnetic waves. And the efficiency of the radiation will depend on the dimensions and design of the conductor. Now, here's an equation. We don't need to know it. It just says, and it's fairly obvious, that the efficiency of an antenna is how much is radiated over how much is input. So if, for example, 9/10 of what you put in was radiated, then the efficiency would be 9/10, 0.9, or as a percentage, 90%. And it may also be self-evident that an efficient antenna will have a high return loss because most of the energy, a high proportion of the energy, will be radiated and therefore not returned back down the feeder. But that's just an ancillary point. An example that I found on the internet, a steel rod of 1.5 meters and diameter 1 millimeter at 100 megahertz was calculated to have an ohmic resistance of 3.4 ohms and efficiency of 95%. So there you can see that the efficiencies that you're looking for in antennas are typically quite high. We want as much power to be radiated as possible. So nothing to be learned here. This is, again, just background. Throughout our studies of antennas, it's generally the half-wave dipole that's the standard antenna from which the other antennas are often gauged. And in fact, when we're looking at the gain of antennas, we either quote the gain in dBi or dBd. dBi being with respect to the isotropic, which is a mathematical antenna, if you like, a single point source that radiates equally in all directions, a bit like a little tiny glowworm light at the center of a glass sphere, illuminating the sphere equally. Or we quote it in dBd, decibels with decibels of gain with respect to the half-wave dipole. And it is probably worth memorizing the fact that a half-wave dipole has 2.17 dB gain, approximately 2.2 dB gain, on an isotropic radiator. So we'll have a little look at that in class a bit more. But sometimes you'll see a yagi, for example, might be quoted as having a gain of 6 dB, 6 dBd, or that would be 8.17 dBi. So there we go. Right, so the half-wave dipole, if you like, is the reference antenna which we keep going back to when we're sort of gauging how things are doing. Let's have a look at the half-wave dipole. Here's the current and voltage distribution on a lambda by 2 dipole. You can see at the center the voltage is 0, and in this stage of the cycle we've got a positive V and a positive I, and this is simply positive, just simply means it's going in one direction for the I, you know, in the antenna there. In the next half cycle, we would expect both of those to reverse. And you can see animations on the internet showing how the voltage and the current distribution changes with each cycle of RF energy applied to the antenna. Now, it's worth noting here that the voltage and current distribution is independent of feed point. So whether you feed it from the end or feed it from the center, the voltage and current distribution is the same. Let's have a little look at the center of it. Here we see that the voltage is 0 at the center, or very close to 0, and the current is high. So that implies that the impedance, Z equals V over I, something low over something high, is low. And in fact, the theoretical figure there is 73 ohms, very close to the 75 ohms that you see for feeders, or some feeders. If we have a look at the end of the half-wave dipole, we've got a very high V and a very low I, and at that point the impedance is very high. If the I was actually down to 0, of course we'd have infinite impedance, or it would look like an open circuit as we connected our feeder at that point. So feeding a half-wave dipole, we've established that where we connect our feeder will determine what sort of feed impedance we're going to be looking at. And that's important if we want to correctly match to the antenna. So we center feed it. We think that the impedance is going to be quite low, somewhere around 73 or 75 ohms or something of that order. That may not be suitable for us, although we have 75 ohm coax. Remember that the half-wave dipole is a balanced antenna, and therefore, if we're going to connect to it with 75 ohm coax, for example, we're going to need some sort of balun to change the unbalanced coax into convert the unbalanced coax into a balanced feed at the antenna. So we might want to use something like ladder line, a balanced feed, and for that we see typical impedances of 300 or perhaps 600 ohms. So if we move the feed points out a little bit from the center, if you recall the voltage and current distribution points, the V over I will increase from, the V will certainly increase from 0, and the I will decrease as we move from the center in each direction. So if we judiciously move the feed points out slightly, we will see a better match, and that's called the delta match because of the shape of it, a bit like a delta, like a river delta. And then for UHF and VHF, quite often a gamma match is used. And there we see the half-wave dipole mounted on a boom, and the coax braid is connected to the center of the boom, and the center of the coax is connected to an adjustable tube capacitor, and that in turn connects to the one arm of the half-wave dipole at an adjustable tap point. So the capacitor there is to take out any residual inductance that we may experience, and the tap point will determine the impedance. So these are three that are mentioned in the book Advance, and I would recommend that you have a little look at those. They are on page 74, and there is a discussion there about them. But I think we've covered most of the points. We don't need to do any calculations around this in terms of determining where the tap point is. It'd be more common to, frankly, use some software to determine those values. So let's have a look at the implemented length, or the physical length, of a half-wave dipole. Now, we know that in free space, the speed of electromagnetic radiation, the speed of propagation, is 3 times 10 to the 8th meters per second. And that in air, it's not much different. So for all intents and purposes, we once again use 3 times 10 to the 8th meters per second. But we've also looking through the video on feeders, we know that electromagnetic waves in conductors travel much slower, and we call this the velocity factor. Also, at the end of an antenna, there is a capacitive effect. All of this combines to us needing to adjust the physical length of the implemented antenna. So, recapping, velocity of electromagnetic waves in antenna is less than in air, and the capacitance, the end fittings, the ground and nearby objects also affects its electrical characteristics. So, taking these two things together, we apply a correction factor, and typically we cut the antenna to 95% of the free space length, and that's a figure that you could remember. Additionally, there is a formula that you can use, and it's a shortcut for the half-wave dipole. It only applies to the half-wave dipole. You can take the length of the antenna is 143 over the frequency in megahertz. So that's easily derived. If you take the length of the antenna as being, it would be 150 over the frequency in megahertz instead of 300, as in 3 times 10 to the 8th. It would be 150 over the frequency in megahertz, because the 10 to the 8th at the top cancels out with a 10 to the 6th at the bottom. If you want to go through the derivation of that, page 75 of the book goes through that, or you can simply remember it. So for 143 megahertz, the length would be 1 meter. You would expect it to be 1 meter at 150 megahertz, not 143 megahertz. Right, moving on. The radiation shapes. Now we're going to have a look at the radiation shapes of antennas. If you imagine an antenna out in deep space, clear of any objects, or at least several wavelengths away from any other obstructions, not necessarily in deep space, but certainly without taking into account any other obstructions, then the pattern is going to be a toroid or a donut with a dipole as its axis. Now this donut looks something like that, and there you can see the dipole at its axis. Now we can draw this graphically to show what it would look like if we take the top view. If you look down on a donut, you'll basically see a circle. So there is the polar diagram, or the radiation pattern, of a half-wave dipole looking from the top, a vertical half-wave dipole looking from the top. And similarly, if you look at a donut from the side and you cut it along the center, because you want to see where the half-wave dipole is, you'll be presented with two circles, two cores, if you like, of the donut facing you. And so that would be the vertical or side view polar diagram or radiation pattern, if you like, of the half-wave dipole in clear space. Now, if we rotate it and make it a horizontal dipole, simply the patterns reverse. What was the horizontal is now the vertical, and what was the vertical is now the horizontal. So we look at it side on. Again, if you cut it along the big one. If you look at the top view and you cut it along the dipole, you will see the two circles. And if you look at it side on, and the picture isn't quite side on, you'd have to rotate it around horizontally a bit further, you will see the circle. Now, if you bring this horizontal dipole down to near ground level, such that the bottom half of the E and the M fields, the E and the H field, the electrostatic and electromagnetic fields are cut off, then as the ground rises to meet the antenna, or the antenna descends, you'd expect to see a vertical side view as shown there on the screen. But this isn't the case, because the ground has an effect on the antenna radiation pattern itself. So while the horizontal view isn't particularly changed, the side view is changed and looks much more like this. Now, the closer the antenna is to the ground, the closer the main lobes there are, um, are more vertical. And as the antenna is lifted further clear of obstructions, the lobes are established more towards the horizontal. So there's the direction of maximum radiation, sometimes called the takeoff angle, and this was what was referred to then in the syllabus. The effect of the height above the ground will determine the direction of the maximum takeoff angle. If you look on the internet, there are some diagrams of horizontal and vertical antennas at various heights, and it depicts the lobes. There's not always just three, sometimes multiple lobes established as you raise and lower the antenna, and the picture changes. But the main lobes, the direction of maximum radiation, as you raise the antenna, the angle of incidence then drops down, so that the takeoff angle is flatter, and that's a point to remember. So what we've said here is that there is what you might imagine the ideal to be, that semicircle, as the ground has risen up, but in fact the influence of the ground on the propagation of the signal itself modifies the radiation pattern on the side view, and the lower you get, the higher the angle of maximum radiation. Let's have a look at the quarter wave or ground plane antenna. And there we have a quarter wave active element, if you like, just the center of the coax extended vertically. And because we don't have any ground nearby, this may be an elevated antenna, then the braid is brought out and attached to radials. And the radials provide, if you like, the ground plane. That's why it's called a ground plane antenna. You can have a look at the quarter wave ground plane antenna on page 75. It has the symmetry of a cut in half wave dipole, and the ground plane, or in this case the radials, act as a mirror. So that sort of provides, if you like, the theory behind the antenna. And again, on page 75, you can read some information about that. The vertical radiation pattern of a ground plane antenna would look something like that, ideally, if you imagine it, but actually the modification of the ground then establishes two lobes, and once again we have direction of maximum radiation there. The vertical, going back to that one, the horizontal pattern, by the way, is simply a circle. As you might imagine, in the horizontal plane, it's an omnidirectional antenna. The 5/8 whip, remember that in order to get a reasonable match, it's better to have a multiple of a quarter wave, and 5/8 is not a multiple of a quarter wave. So the electrical length of the 5/8 is increased due to the inductance of the tuned coil there. And the tuned coil is electrically 1/8 lambda long. And you can see the current distribution there across the length of the antenna, sort of the main radiating part of it towards the center of the antenna. So it's a fairly efficient antenna, but of course 1/8 lambda radiation is crammed into a shorter physical length, hence the kink there in the current distribution graph. So the next antenna we're going to have a quick look at then is the folded dipole. Now, the folded dipole is a half a wavelength long physically. So that's from tip to tip, if you like. So the length of actual cable then is closer to a complete a wavelength. So despite the name folded, it isn't, if you like, a half wavelength long and then folded down to a physical length of a quarter. It's still physically end to end, if you like, a half a lambda long. Because it's folded then, it does present a high feed point impedance. So for the same power, the feed current is halved and the voltage is doubled. So if we double the voltage and halve the current, then we are multiplying the impedance by 4. So it was 73 ohms, if you remember, the theoretical impedance for a half-wave dipole. Multiplied by 4, it is now 292, or very close to 300 ohms, which is a great impedance to have for a 300 ohm balanced ladder line type feeder. The next antenna we'll have a quick look at will be the yagi antenna. There's the yagi antenna, it has a boom in the center. It has a driven element shown there with the feed point, and it has some directors, any number if you like, going forward. And behind the driven element is a reflector. The driven element is called the driven element because it's the only one that is driven by any power directly, and here we show it connected to a ladder line. The function then of the reflector is to reflect the power forward, and it's constructed to be about 5% longer than the driven element, and this creates the appropriate phase in the waveforms generated to reinforce the signal in the forward direction and cancel it in the reverse direction. So that tends to squirt the power in a forward direction with respect to the axis of the yagi. The driven element will be, of course, lambda by 2, or it could be a folded dipole. It's quite often used on a yagi, and that'll be corrected for velocity factor and end capacitance. So it'll be about 95% of the free space calculated length. Each director then, the directors work similarly to the reflectors, but they help to focus, they're cut to focus the power in the forward direction. Each one is about 5% shorter than the previous element, and the spacing between them is about 0.15 lambda. So that's the yagi antenna in terms of its construction. In terms of drawing its polar diagram or its radiation pattern, if we place the yagi antenna at the center, if you like, of our diagram, and then plotted on the diagram points of equal field strength. So practically speaking, if we were over a nice flat area, we'd walk around with a field strength meter, plotting on a map points of equal field strength. This is the pattern we might achieve. You can see the main lobe is in the forward direction. There are some side lobes and even a back lobe, but by far the main lobe is in the forward direction, and this is a function of both the reflector pushing the power in the forward direction and the directors providing a focusing effect on the waveform, on the wavefront. So if we drew a circle then, and we call that arbitrarily 0 dB, and then we walked back into the closer to the yagi and said where is a point of minus 3 dB, in other words 3 dB lower than that, then there we could draw points where our lobe intersected the -3 dB points, and we could construct straight lines through those, and that gives us our beam width. That's our beam width at the -3 dB or half power point. That means that if we rotate the antenna through half of the beam width, then a stationary receiver will then receive half the power that it was receiving. Make sure that you don't confuse beam width with bandwidth. These are entirely different concepts. Beam width here is the half power points, not like bandwidth, if you like, when you're looking at the Q, you know, for filters and things, although it is similar, I suppose, but it is conceptually different. This is a physical rotation of the antenna through half of the beam width. If you imagine that on the diagram, then you would see that you would be getting only half the power to a receiver located somewhere on the right-hand side of the screen. The next antenna we're going to have a look at is the quad antenna, so called because it has 4 sides. Each side is lambda by 4, and it's constructed in that way. Now, the antenna, as you can probably guess, is a balanced antenna with a 100 ohm feed. If we put a reflector behind the quad, in the same way as we do with a yagi antenna, then the reflector once again would be approximately 5% longer on each side, and the effect of the reflector would be to reduce the bandwidth down to about 75 ohms. So this goes back into the point about adding other elements to an antenna, such as a quad or yagi. The general effect then is to reduce the feed impedance. This is why a folded dipole is quite often used on a yagi, because you start off with 300 ohms perhaps, but by the time you put in a few extra elements, it helps to reduce the impedance. So a single antenna for 2 frequencies. Now, if we imagine we had a requirement to have a 14 megahertz antenna, it might look something like that. And then if we had a requirement for a 7 megahertz antenna, it might look something like that. But space constraints might mean that we wish to combine the two together. If we tried to end feed the 7 megahertz antenna, we would have very, very high impedance, you know, for 14 megahertz if you like, and it wouldn't be terribly efficient. So if we imagine that, for the sake of notation then, that the 14 megahertz antenna frequency f2 would have corresponding wavelength lambda 2, and f1 for 7 megahertz would have corresponding wavelength lambda 1. And we can join them together. Now, if we put a special device, which we put in red there, which allowed at the feed point the antenna to appear like a 14 megahertz antenna when we were tuned to 14 megahertz with our transmitter or receiver, but it also appear like a 7 megahertz antenna when we were tuned to 7 megahertz, that would be ideal. And in fact, that's what happens. It's called the trap dipole. We simply take our antenna, make it shorter so that it's fine at lambda 2, or in our case 14 megahertz, and we put in parallel tuned circuits. And these are added, and then further length is added after the parallel tuned circuit to make it okay on at lambda 1. So electrically then, the trap is resonant at f2. So the trap is resonant at 14 megahertz. So if you can imagine 14 megahertz being applied to this antenna, the transmitter would see, if you like, a lambda 2 by 2 or 14 megahertz half-wave dipole, because anything beyond the end of the first length is high impedance at 14 megahertz. Remember, parallel tuned circuits or tank circuits are high impedance at their resonant circuit. So this makes the rest of the antenna effectively invisible. But if we reduce the frequency down to 7 megahertz, then the resonant circuit or the parallel tuned circuit is no longer resonant. It was resonant at 14 megahertz. It is not resonant at F1. It simply looks like an inductor. So in fact now at 7 megahertz we see the full length of the antenna, and in fact a bit more than the full length of the antenna, because we're seeing some inductance in each leg. So for that reason the full length of the antenna is adjusted to make it electrically look like a 14 megahertz antenna, I beg your pardon, a 7 megahertz antenna at that frequency. So that's the trap dipole. It doesn't necessarily have to be 2 traps and just work on 2 bands. It could have 4 traps, in other words 2 on each leg, and that would make it work on 3 bands. So there are some questions I've seen in the RSGB exams which say, for example, a trap dipole has 2 traps on each leg. How many bands will it operate on? And it's tempting to write 2, of course, but with 1 trap it works on 2, with 2 traps it works on 3, and you can draw this out yourself and get yourself familiarized with that. Okay, moving on then to end-fed antennas, and let's have a look at the end-fed antenna. Now you would use the end-fed antenna when the house and garden layout favours that sort of construction. And if you can imagine, then you've got a house and a convenient pole or tree, then it is quite convenient sometimes to hang a lambda by 2 antenna from the tree, obviously using insulated end insulators and insulated rope, not connecting directly to the house or the tree, and the insulators are shown there as blue circles. But it's useful to hang a lambda by 2 between the tree and the house. Now, if we do that, we will find that we will end up with a high feed impedance at the end of a half wave. Now, if you go back to the earlier slides, and by the way, these are posted to the shared drive, and you look at the current and voltage distribution along the lambda by 2 antenna, and if you also recall that they are independent of the feed point, you will see that at the end of the half wave you have got high feed impedance. So high feed impedance implies a high voltage and consequent risk of EMC interference. So we need a circuit in there to provide our matching, and this is the sort of circuit we might use. Because it's high feed impedance, a parallel tuned circuit, which has high impedance, is indicated, and the capacitor that is there to make the load resistive, because it'll be quite inductive otherwise. And the variable taps on the transformer are then to match this high load, which after adjustment with the capacitor is resistive, but match that back to the feeder and ultimately the transmitter. So that's the end-fed lambda by 2. Let's have a look at an end-fed lambda by 4, maybe particularly at bands like top band, where or 80 meters. A quarter wavelength is still a considerable length, and the house and garden layout may indicate a quarter wave antenna is all you have room for. So a quarter wave antenna is quite acceptable, and there it is, hanging between an appropriate post and the house. Now, with a quarter wave antenna, you will have a low impedance feed, and that means low voltage. You expect a low voltage across a low impedance, but a high current. Again, high current will flow into a low impedance. So you must have a good earth, a very good earth, otherwise the rig and the shack may be at high voltage. And because you've got a low impedance, a series tuned circuit is indicated, and that will help to, the capacitance then will help to make it resistive. Because you need a good earth, it indicates that the shack can probably only be at ground level or ground floor level, because to have a long vertical earth coming down the side of the house or internally into the house would add to the resistivity of the earth, and if the resistivity of the earth approaches the resistivity of the feed point, then the earth itself becomes a radiator. So that would not be desirable. So you need to have a very, very good earth, very short and direct earth, if you're going to employ this sort of setup. So once again, probably a ground floor only shack if you're going to use a lambda by 4. Let's talk a little bit about the positioning of loading coils. If we had a lambda by 8 antenna, so we say here if an antenna is less than lambda by 4, it will be highly capacitively reactive, and current will not have risen up the quarter wave or the sine wave before it reaches the feed point. So we're saying that lambda by 8 or anything much less than lambda by 4, the waveform won't have time to establish before the other half cycle comes along. And so the overall current will be less. And here in this example we've said there's a 5 amp current feed. Now with this setup, you need to increase, if possible, the electrical length of that lambda by 8 to get it to be closer to lambda by 4, so that or greater, so that the current will have time to fully establish in both of its half cycles. So here we have it. We've added a loading coil, and if we look at the current distribution now compared to what it was, we've managed 8 amps instead of 5 amps because we've managed to establish the current on each half cycle. And you can see that the main current is established along the radiating part of the antenna, which will give us greater efficiency in our antenna operation. And you can see that the current distribution is crammed up, if you like, in the loading coil at the end. Now it's better to locate the loading coil towards the end for the reasons we're going to discuss now. So we can say if an antenna is less than lambda by 4, it's useful to increase the electrical length of the loading coil so that current can establish. But putting the coil, to match the capacitance of the antenna, at the non-feed end will ensure that this current in the radiating part of the wire is minimized. We would have had a minimum current in the far end of the wire anyway, so if there's ever a place to cram up the radiating elements, then do it in the low current part rather than in the high current part of the antenna. So that is a very quick tour through antenna. It doesn't cover it as thoroughly perhaps as the chapter 10 in advance, but it does discuss a couple of points which may be, which hopefully it's made a bit clearer, but I do recommend that you read chapter 10 thoroughly. Areas that you do need to cover are, for example, putting in traps in beams. If you have a beam or a yagi, you will not only need to put traps in the driven element to alter its electrical length, you will need to put them into the reflectors and directors as well to alter their physical length. So now we move on to antenna matching units or antenna tuning units, and the terms are used interchangeably. So let's have a look. There is a general form of the antenna tuning unit. It adds capacitance or inductance to the system to make the overall load resistive. And there you can see you've got a capacitor across the transmitter directly, an additional capacitor then in series with that, both across a variable inductor, and then finally a third capacitor going off to the antenna. Now, this also matches the impedance of the transmitter to the load, and it provides an extra layer of harmonic filtering, but you should not rely on this for your harmonics filtering. This is, if you like, just belts and braces. There we see what can happen in a parallel tuned circuit. Circulating currents in parallel tuned circuits can produce high voltages and currents, so that's something to watch out for from a safety point of view. And also, you need to be very generous with your component tolerances. These high voltages will jump across veined capacitors if the spacing between the capacitor plates is not great enough. So let's have a look at one more specific form, the L match, so called because the capacitor and inductor form a sort of L shape. So there the general configuration of the L match. If we have a look at the top version, the L match is placed at the antenna, and it matches the antenna to the feeder, thus reducing the VSWR in the feeder. And that's very good for EMC reasons, and also it's nice not to have a high VSWR in the feeder. The difficulty is, of course, that if your antenna is remote from your radio, which it usually is, it implies that you have to have an automatic tuner at the top of the mast or at the feed point, and this has to be controlled electrically by various devices to switch in and out the capacitance to make it operate. And you can see commercial versions of this, one made by ICOM, for example. Similarly, on things like yachts and things like that, they tend to try and match, have a masthead antenna tuning unit. The bottom version is more convenient. It's in the shack, but it does leave a high VSWR in the feeder. So there we go. Yeah, so the L match placed antenna matches the antenna to the feeder, thus reducing the VSWR in the feeder, but the one in the shack, although it matches to the transmitter and SWR meter, it does leave a high VSWR in the receiver. Let's have a quick look at the pi match. Now the pi match is so called because it's shaped like the letter pi. If you use your imagination a bit. And it uses a variable capacitors, but also a variable inductor. And that variable inductor is constructed a bit like this. There's a large coil around a former and a knob on the end of the coil, two end plates to allow the knob to rotate the coil, a conducting metal strip insulated from the end plates, on which is a wheel, and that wheel slides up and down the coil. So between the wheel and the coil, end of the coil, which is quite often attached to the spindle, you've got variable inductance. So rotating the coil allows you to, while the coil is active with perhaps 5 watts on it, you can tune for minimum VSWR. And this is called the roller coaster inductor. And that's physically what it looks like when you see one actually constructed. It provides a wide range of tuning and is therefore quite useful. Here we have the T match. This is less commonly used. It can either be a T formed with 2 inductors at the top or 2 capacitors at the top. It has the advantage that it may provide better matching in high impedance circuits. So you do see T-match used, where you have a high impedance circuit. And where may you have a high impedance circuit? Well, for example, if you're end feeding a lambda by 2 dipole. The top version only, because we've got series inductors, and series inductors act as a low pass filter. So that may also be of use, although once again you shouldn't rely on your matching circuit to provide your attenuation of harmonics. You should instead have a separate harmonic filter on the output of your transmitter. But for belts and braces, it also acts as a low pass filter. Finally, we have a small discussion here, and again, I think we'll talk about this more in the propagation video, which I'll produce in due course, but direct and reflected waves. So there you see the end of a half-wave dipole and the incident ray going off into the sky, but also a ray going down to the ground and then being reflected off. And these two rays will combine either in phase or antiphase, or sometimes variably, for example, with the rising and falling of tide, to either augment or decrease the signal at the receiving end. So this has to be taken into account quite often with things like microwave links over water, where the reflected ray can cause fading with the movement of the water at the receive end. And there is a short discussion about this in chapter 10 in advance. As I say, we will be going through this in a bit more detail later on. So most antennas will radiate some energy towards the ground, and this will combine with the direct ray. So that pretty well sums up the chapter 10 of the book Advance. I would encourage you to read through it. I think of particular importance is the voltage and current distribution in the half-wave and quarter-wave dipole. With a bit of practice, you can figure out what's happening if you can construct those diagrams from memory, or at least from first principles. That will pretty well allow you to answer most questions and figure out what's going on. So thank you once again, and I look forward to producing the treatise on propagation shortly.